Okay, and the last talk is timing channels in adaptive neural networks. And the speaker, Ayomide Akinsanya.
Yep.
Okay. So the stage is yours.
Hello, everyone, and thank you for coming to our talk. Today, I'll be presenting joint work with my advisor, Professor Tegan Brennan, on timing channels in adaptive neural networks. Okay, sorry. Okay, so different applications contain secrets such as user inputs to the applications and also user passwords and even crypto keys that the applications use to process inputs to outputs. And attackers are always incentivized on how they can steal such secret information. And one way an attacker can do this would be to try to directly hack the application by leveraging some malware or some software bug in the application. Another way the attacker can do this is to exploit some non-functional characteristics of the application, such as how long it takes for the application to run or the amount of power consumed by the application while it's running. It is these non-functional characteristics of the application that we refer to as side channels. I'm sure many of us are familiar with different side channels attacks, such as Spectre and Meltdown, that greatly affected a great number of Intel CPUs, and also power side channel attacks that were used to leak secret bits of an RSA key, and other software side channel attacks. In this work, we are mainly focused with timing side channel attacks, also known as timing channels, which consider how variations in an application's runtime can allow an attacker or an adversary to leak secret information about the application. Our main contribution in this work is to show that timing side channels can arise in adaptive neural networks, and that these timing side channels can leak confidential information about inputs to the adaptive neural network. In order to understand our work, let's first understand how conventional neural networks work. So for a typical conventional neural network, we have different images that are fed to the neural network and are fed sequentially through the network in order to get a classification on the output. But in the case of adaptive neural network, especially for like early exit networks, we understand that not all inputs are the same, so not all inputs require the same amount of computation. Thereby, this type of adaptive neural networks are embedded with early exits to classify some inputs early once the model is able to deem that it's confident enough to classify it. For an example, take for example the image of the front-facing dog. This image is clearly obvious to everyone in the room that this is a dog, and the adaptive neural network is able to understand this complexity and classify the image early via exit 1 as an image of a dog. In the next example, we see an image of a dog lying down on the floor, and this is a more challenging example, and the adaptive neural network is also able to capture this complexity and classify the image as a dog via exit 2. Finally, we'll see a more challenging image of a dog rolled up on a blanket. And this is not very obvious that this is a dog in this image, as it could be a bagel. So our adaptive neural network is also able to capture this complexity and classify the image via exit 3 as a dog. And notice how in the 3 different scenarios, our adaptive neural network can use variable amount of computation based on the difficulty of the inputs. So why adaptive neural networks? As we saw earlier on, that typical neural networks treat all inputs the same. That is, they are unable to differentiate between complexities of different inputs. But in the case of adaptive neural networks, they can understand this complexity and treat them differently and use like variable amount of computation for them. And as a result of this, adaptive neural networks are able to achieve lower computational costs and also achieve faster inference times. And because of their lower computational cost, adaptive neural networks can be deployed on smaller devices and resource-constrained devices, such as edge and IoT devices. So let's take a look back at our adaptive neural network that we saw earlier. Let's notice how this adaptive neural network resembles the control flow graph of a program, and how the 3 different exits correspond to 3 different return statements in the program. From our study of side channels in software, we know that this type of structure in a control flow graph can result to timing side channels. But in order to, and it's also like very practical or very logical to assume that these 3 different exits would also partition the input space to the adaptive neural networks into 3 groups, depending on like the exit where the input gets classified at. And in order to verify this assumption, that this assumption is actually valid in practice, we train this adaptive neural network on a cancer data set. And the cancer data set is a data set that consists of images of benign and malignant skin moles. And the goal of this adaptive neural network is that given an unseen skin mole image, to predict the diagnosis of the skin mole, whether or not it's malignant or benign. And also, we want to note that the predictions of the model should be private. That is, when I send an input skin mole image to the adaptive neural network, only I should be able to know what the model's prediction on my input is. Other users shouldn't be able to figure that out. So there are 2 major questions we would like to answer. And the first question is there a correlation between the inference times of the adaptive neural network and the different exits in the network? Also, if that is true, is there a correlation between any of the attributes in the data, in the input data to the adaptive neural network, and any of the exits in the adaptive neural network? And for this particular example, the attribute we consider is like the class label. So that is, does any of like the class label correlate with any of the exits in the adaptive neural network? So to answer question 1, we plot a graph of the response time of the adaptive neural network and the exit and the different exits in the model. And we can clearly see from the 3 different clusters in the graph that indeed there exists a strong correlation between the different exits between inference times and the different exits in the adaptive neural network. So for inputs that take exit 3, they will definitely have like longer inference times, which our assumptions confirms. So the second question is that if there exists like any correlation between a particular class label or attribute of the input with any of the exits. And we can clearly see that from the image on your left, that there exists a strong correlation between the benign class label and the timing interval that corresponds to taking exit 1. So that is, whenever we see a timing measurement that corresponds to an input taking exit 1, we can kind of infer with a stronger probability that that input is a benign skin mole. And for this, we consider this like a privacy violation. So when can this be a problem? We consider the following threat scenario whereby we have different clients querying an adaptive neural network with their inputs, and they hope to get like predictions back from the model. And we consider an adversary who is also a client of the model and can also send inputs to the model and obtain predictions back from the model. We make the following assumptions for our adversaries: that the adversary can send their own queries and get predictions, and also that our adversary can sniff packets over the network using some packet sniffing tools, such as Wireshark or TCP dump. But then we also enforce the fact that the attacker cannot decrypt these packets because we assume that the communication is encrypted end-to-end. But then the attacker can leverage packet properties such as packet timing and also like packet directions that they are able to capture. So what does the attacker aim to learn? As we saw in the earlier example, the attacker aims to obtain a sensitive attribute or an attribute of the user input. And in this particular, in the case of our cancer example, the class label of the input, whether or not it's malignant or benign. So how does the attacker do this? In order for the attacker to do this, the attacker first of all generates a timing profile of the model. And the attacker does this by leveraging a manifest data set. The manifest data set is a data set that belongs to the same training distribution, belongs to the same distribution as the original data set that the model was trained with. And the attacker can easily obtain this data set by scraping the internet for images that correspond to this same distribution, or like corresponds to the distribution of like the particular goal of the application. And the timing profile that the attacker is able to obtain is just a mapping of timing measurements of input samples in the manifest data set to their sensitive attribute, which is like the class label. The attacker then trains an attack model using this timing profile. The attack model we used in our work was just a simple neural network, but other models can be used, like a logistic regression model or even decision trees. And then the attacker then leveraged this trained attack model to infer the sensitive attribute. So that is, once the attacker is able to capture the timing measurement of a victim's input to the adaptive neural network, the attacker can then infer what the sensitive attribute of the user is from just the timing measurement. So in order to evaluate the success of the attacker, we adopt the following metric. The first metric we adopt is the attack success rate. And this metric has been used in previous attacks on machine learning models, such as membership inference attacks. And in the case of membership inference attacks, the attack success rate just corresponds to the accuracy of the model to infer whether or not a particular input sample belongs to the training set or not. But in our own particular case, the attack success rate corresponds to the accuracy of the model to infer the sensitive attribute of a user's input, given their timing measurement. But then, from the earlier example that we saw, since that we saw that some particular exits or some particular time clusters or time intervals can have stronger correlations with certain exits in the network, this led us to define a new metric, which we denote as the attack success rate per cluster. And the attack success rate per cluster just corresponds to the accuracy of the attack model to infer the sensitive attribute of a user whose timing measurement falls into a particular time cluster. And in order to obtain the different clusters of the model, because we assume that the attacker doesn't know how many exits are in the model, we partition the timing profile of the adaptive neural network using kernel density estimation, also known as KDE. And for our experiment, we perform timing measurements over a local area network, and then we train 6 different adaptive neural networks, 6 different variants, as you can see on the screen. And then we train these 6 different adaptive neural networks across 4 different data sets. We consider 3 attributes, which are mainly class label, the generalized class label, and also whether or not an input is adversarial or not. So can find our result, our complete result in our paper. This is too much information, so I'll just highlight some of our results. For the case of RNet trained on the cancer data set, we're able to find clusters with an attack success rate of 95.05%, which comprise 23.35% of the input distribution to the adaptive neural network. And what this means is for about 23% of inputs of users querying the model with their inputs, we are able to infer with an accuracy of 95% their sensitive attribute. Also, for block drop trained on CIFAR-10 dataset, we're also able to find a cluster with an attack success rate of 98.94%. But although we see a smaller input distribution that is compromised in this case of 4.8%. We also find cases where we do not find clusters with significantly high attack success rate. For example, the branch AlexNet trained on the CIFAR-10 dataset. Other things that we considered in our work was to understand the effect of hyperparameter tuning on our attacks. And the major hyperparameter tuning for early exit networks is their exit thresholds, which controls how confident the model is in classifying an input at certain exits in the model. So we considered 3 different settings: the conservative setting, the balanced setting, and the relaxed setting. In the conservative setting, we are enforcing very strict thresholds on the exits. And this particular setting favors whereby we favor accuracy over efficiency. That is, we want the model to only classify an image at an early exit when it is really confident about the class of the input. So in this setting, we find clusters with significantly high attack success rates, but then we find that the efficiency of the model is reduced. While in the relaxed setting, we do not find clusters with significantly high attack success rate, but then this comes at a reduced accuracy of the model, but better efficiency of the model. Some other interesting observations that we see that for our adaptive neural networks trained on the cancer data set, we kind of see a similar agreement across their first exits that the benign skin mole images are easier to classify at the first exit compared to the malignant skin moles. We also see similar agreement on the Fairfax data set, whereby the different models agree that images or faces of users who are within 0 to 19 age groups are easier to classify than other age groups. So in conclusion, we've been able to demonstrate how timing side channels in adaptive neural networks can leak private information. We've also been able to show how an adversary might leverage such timing side channel leakage. And we've been able to experimentally validate our technique across 6 different adaptive neural networks and 4 data sets, considering 3 different attributes. And finally, we've been able to show how hyperparameter tuning, such as exit threshold, can result in trade-offs between accuracy, efficiency, and privacy. All our results are available on the GitHub repo on the screen, and they are functional and they can be reproduced. Thank you very much.
Thank you. Questions?
Hello, and if the cloud model has an unstable network delay in the processing of returning the result, will your mentioned approach still work?
So for those type of scenarios, because we also, in our paper, we conducted experiment over like the public internet as well, whereby we deployed the adaptive neural network on a Google Cloud server. And even when we see that there are like delays which can be attributed to like noise in the network, we can still find like clusters with very good attack success rates. Although like the accuracy in this particular experiment was reduced, but we could still find like clusters with still very good accuracies of our model, attack model. Yeah.
Oh, okay, thank you.
Very cool. I'm just curious, how well does your results generalize when you take into consideration network latency? Because it seems like you're picturing a cloud like serving DNN from the cloud, whereas your setup is a local area network, right? When you're dealing with like Microsoft, like network latency is obviously much more fuzzy, right? And they also have like a bunch of scheduling tools there that do not just run your inference immediately, right? Like the timing is messed up when it's much harder to, it seems to me that it's much harder to predict when you're actually getting results from a Microsoft cloud, right? Because they have all kinds of optimizations there and they do not necessarily run your inference task immediately. I wonder how well your results generalize to those cases.
Yeah, so I kind of agree with you that in case of like when the other cloud provider is running like some optimizations, which further like maybe make the model like inference faster, that could like mess up like the timing measurements. I kind of like concede that as well, yeah.
Maybe I can add to that, because we have seen remote attacks on crypto algorithms where they have to solve the same problems and they were shown effective. So I won't be surprised that if it were shown to work as well over normal networks. So the next question.
I'm not sure if I just missed the key part. So this attacker seems to have access to a distribution that is very similar to the model's training data. If that's the case, and then your argument was that these distributions can be crawled from public. If this is public, is there any privacy issues if the distributions are the same?
It's not really privacy issues. So for example, in the cancer data set, one could just check the internet for other labeled samples of data sets that correspond to cancer and different diagnoses as well. So one could leverage such data sets which are not anonymized to belong to any particular patient. So it's really not a privacy issue in that sense. Yeah.
And maybe final question from me. So obviously in adaptive networks, this timing effect manifests more strongly. Did you try to experiment with normal, non-adaptive networks? Did you get anything there?
Yeah, so in our paper, we also did experiments on non-adaptive neural networks as well, and we don't find any clusters with significantly high attack success rates. Yeah.
All right. Okay, thank you. Okay, thanks. Let's thank the speaker.